Event Report: Google Willow vs Microsoft Majorana 1 in Quantum Computing. Date: February 25, 2025. Time: 18 hours 41 minutes and 33 seconds. Introduction. As the race in quantum computing escalates, two prominent players, Google and Microsoft, are at the forefront with their respective projects, Google's Willow and Microsoft's Majorana 1. This report delves into the nuances of each technology, their methodologies, and the implications of their advancements on the quantum computing landscape. Technology Foundations. 1. Google Willow. Qubit type: Google Willow employs superconducting transmon qubits. These qubits function optimally at temperatures close to absolute zero, necessitating advanced cooling technologies. Processor architecture: building on the foundation of the Sycamore processor, Willow aims to enhance the scale of qubits to over 105, focusing on robust error correction mechanisms. Cooling mechanism: it utilizes dilution refrigerators, a common cooling method in superconducting qubit systems, to maintain operational conditions. 2. Microsoft Majorana 1. Qubit type: Microsoft's Majorana 1 introduces topological qubits based on Majorana 0 modes MZMs, which are distinguished by their potential stability and lower susceptibility to errors. Design philosophy: Majorana 1 incorporates a topological core designed to minimize software-based error correction by leveraging the inherent stability of topological qubits. Cooling mechanism: similar to Willow, Majorana operates at low temperatures but is engineered for compactness, allowing it to fit into smaller physical spaces. Qubit count and stability. Google's strategy revolves around expanding the number of qubits to bolster error correction capabilities. This approach requires multiple physical qubits to create a single logical qubit. In contrast, Microsoft's architecture allows for a more efficient qubit usage, where 8 physical qubits can yield 1 logical qubit, potentially leading to more stable computational results. Error correction strategies. Google Willow: the focus here is on scaling qubits to improve error correction performance. Google has demonstrated significant advancements, such as completing a complex quantum task that would take a classical supercomputer an estimated 10 septillion years in merely 5 minutes. Microsoft Majorana 1. Majorana 1's design naturally resists errors, allowing for precise control over electron interactions through a novel measurement technique. This capability enables the detection of minute differences in electron states, even in systems containing vast quantities of electrons. Scalability and commercialization. Google has laid out a roadmap to gradually scale to over 10,000 qubits by the early 2030s, with application targets including drug discovery and simulations for nuclear fusion. Microsoft, on the other hand, has set an ambitious target of achieving 1 million qubits by 2027 to 2029, with aspirations in areas such as environmental remediation and advanced materials. However, skepticism surrounds this timeline given past overestimations regarding Majorana qubits. Industry impact. The technologies from Google and Microsoft have the potential to disrupt multiple industries. Cybersecurity: both systems could challenge existing encryption methods, prompting a shift towards post-quantum cryptography. Materials science: Microsoft's focus on topological qubits might enhance chemical modeling, while Google's system could optimize energy solutions, particularly in battery technology and nuclear fusion. Cloud computing: both companies are positioning their quantum computing offerings as cloud services, with Google Cloud and Azure Quantum leading the way in delivering quantum capabilities to developers. Expert opinions and future outlook. The perspectives on the viability of both approaches are diverse among experts. Microsoft's Majorana 1: while some researchers express optimism regarding the potential of topological qubits, the full demonstration of fault tolerance remains an outstanding challenge. Google's Willow: the advancements in error correction are recognized as significant, yet the journey towards scaling to millions of qubits continues to present formidable challenges. As the competition progresses, the distinct paths taken by Google and Microsoft may eventually converge, suggesting a future where hybrid approaches could unlock the full capabilities of quantum computing. Conclusion: Google's Willow and Microsoft's Majorana 1 exemplify two contrasting methodologies in the quest for practical quantum computing. Both initiatives promise to pave the way for groundbreaking advancements across various sectors, underscoring the importance of continued innovation and collaboration in the quantum realm. The outcome of this rivalry will likely shape the future of computing, with profound implications for technology and society at large. The competition between Google's Willow and Microsoft's Majorana 1 in the quantum computing landscape involves several counterintuitive aspects that challenge conventional wisdom regarding technology development and scalability in quantum computing. 1. Error correction versus qubit count. Traditionally, it is believed that increasing the number of qubits is the most effective way to enhance error correction capabilities in quantum computing. Google's Willow adheres to this principle by aiming for a significantly higher qubit count, over 10,000 qubits, to improve error correction through redundancy. However, Microsoft's Majorana 1 contradicts this notion by adopting a design where fewer qubits, 8 physical qubits forming a single logical qubit, can achieve similar or even superior stability. This suggests that a focus on qubit quality and inherent stability rather than sheer quantity could be a more effective approach to achieving fault tolerance in quantum systems. 2. Compact design implications. The compact design of Microsoft's Majorana 1, which aims to fit into smaller packages, challenges the prevailing assumption that larger systems are inherently more capable. The ability to create stable topological qubits in a more compact form may lead to more practical applications and easier integration into existing technologies, which is often overlooked in discussions favoring larger scale systems. 3. Scalability timelines. Microsoft has set an ambitious goal of achieving 1 million qubits by 2027 to 2029, which contrasts sharply with Google's more conservative approach of gradually scaling to 10,000 plus qubits by the early 2030s. This raises questions about the sustainability of rapid scaling in quantum technology, as past claims from Microsoft about Majorana qubits have required revisions. The counterintuitive element here is that while rapid scaling seems advantageous, it may not always align with the practical realities of technological development and scientific validation. 4. Error resistance versus software-based error correction. Microsoft's Majorana 1 uses topological qubits that are inherently designed to resist errors, thereby minimizing the need for extensive software-based error correction. This stands in contrast to Google's approach, which relies heavily on scaling and software solutions to mitigate errors. The implication here is that hardware-level innovations can potentially render traditional software-based error correction strategies obsolete, contradicting the long-held belief that software solutions are essential for managing hardware limitations. 5. Broader applications and impact. Both systems are anticipated to disrupt fields like cybersecurity and materials science, but the specific applications differ. Google's focus on drug discovery and nuclear fusion contrasts with Microsoft's emphasis on environmental solutions like microplastic degradation. The counterintuitive aspect lies in the notion that the same technological advancements can lead to vastly different societal impacts depending on the approach taken, challenging the idea of a one-size-fits-all solution in quantum applications. 6. Expert skepticism and market perception. There is notable skepticism among experts regarding Microsoft's aggressive timeline for Majorana qubits, especially given past overestimations. This skepticism highlights a counterintuitive truth in technology development. Bold claims can sometimes overshadow the realistic incremental progress made by companies like Google. It suggests that a more cautious approach may be more beneficial in the long term, fostering an environment where steady, reliable advancements are prioritized over sensational milestones. 7. Integration of approaches. The notion that both companies might need to integrate their methodologies for optimal results is a counterintuitive takeaway. Traditionally, competition drives singular paths to success, but in the case of quantum computing, leveraging the strengths of both superconducting and topological qubits could yield more robust solutions than either could achieve independently. This collaboration over competition could redefine industry dynamics and technological progress. In essence, the competition between Google's Willow and Microsoft's Majorana 1 illustrates several counterintuitive realities in the quantum computing field, challenging established beliefs about scalability, design error correction, and the broader implications of technological advancements. In the ongoing competition between Google's Willow and Microsoft's Majorana 1 regarding quantum computing, certain critical nuances often go unnoticed that can significantly influence the future landscape of this technology. Here are some overlooked aspects of their rivalry along with their implications. 1. The nature of qubits. While most discussions focus on the number of qubits each system can achieve, the inherent properties of the qubits themselves are equally significant. Google's use of superconducting transmon qubits, which require extreme cooling, poses challenges related to scalability and operational efficiency. In contrast, Microsoft's Majorana 1 employs topological qubits, which are theorized to be more stable and less susceptible to environmental noise. This fundamental difference in qubit design could mean that Microsoft's approach may not only require fewer physical qubits to achieve logical qubits but could also offer a more streamlined path to fault tolerance. The significance lies in the potential for Majorana qubits to facilitate quicker advancements in practical applications should they prove to be viable. 2. Error correction mechanisms. Most analyses highlight the error correction strategies employed by each company, but the underlying principles of these strategies can be overlooked. Google's approach, which relies on increasing the number of qubits for error correction, may lead to a scenario where the complexity of managing a vast number of qubits becomes a bottleneck. On the other hand, Microsoft's design aims to minimize the need for extensive software-based error correction through hardware-level stability. The implications of these strategies are profound. If Microsoft can demonstrate effective fault tolerance with fewer qubits, it could lead to faster and more efficient quantum computing advancements, potentially outpacing Google. 3. Scalability challenges. While Google's plan to scale towards 10,000 qubits by the early 2030s is ambitious, the practicalities of achieving this number while maintaining operational efficacy is often glossed over. The scalability aspect is not merely about quantity. It encompasses the ability to maintain coherence, manage entanglement, and execute complex calculations without significant error rates. In contrast, Microsoft's target of 1 million qubits by 2027 to 2029 raises skepticism, particularly given past overestimations related to Majorana qubits. The overlooked significance here is the potential for Microsoft's faster timeline to either destabilize Google's position in the market or to backfire if the anticipated capabilities do not materialize as expected. 4. Potential applications. Discussions typically center on high-profile applications like drug discovery or nuclear fusion. However, the more subtle implications of each company's technology in areas such as environmental remediation or advanced materials are often overshadowed. For instance, Microsoft's emphasis on microplastic degradation and self-healing materials could position it as a leader in sustainability efforts, which could resonate strongly with public and governmental support. This aspect of application could ultimately influence investment and collaboration opportunities, shaping the trajectory of both companies in ways that extend beyond pure computational power. 5. Industry impact and cybersecurity. The potential for both quantum computing systems to disrupt current encryption methods is acknowledged, but the broader implications for cybersecurity are frequently underestimated. The race to post-quantum cryptography is urgent, yet the timeline for both companies to deliver solutions that can effectively address these concerns is ambiguous. If either Google or Microsoft can provide a robust quantum solution before the other, it could significantly alter the security landscape, creating vulnerabilities that could be exploited before adequate defenses are in place. 6. Expert opinions and viability.
The mixed opinions among experts regarding the viability of both approaches often get lost in the excitement surrounding technological advancements. Experts caution that while topological qubits hold promise, they have yet to demonstrate the necessary fault tolerance.
Likewise, Google's advancements in error correction are impressive but may face challenges as they scale.
These expert opinions highlight the precarious nature of both companies' trajectories and underscore the need for cautious optimism rather than blind enthusiasm.
7. Collaboration potential. The competitive narrative often overlooks the possibility of collaboration between the two giants.
As both companies navigate the complexities of quantum computing, there could be significant benefits in sharing insights, particularly in areas like error correction or cooling technologies. Such collaboration could accelerate advancements in the field, ultimately benefiting both companies and the industry as a whole. Conclusion. In summary, the competition between Google's Willow and Microsoft's Majorana 1 is not just a race to achieve the highest qubit count or the fastest processing times. It encompasses a multifaceted landscape of stability, error correction, scalability, application potential, and industry impact.
As both companies forge ahead with their distinct methodologies, the overlooked nuances in their approaches could ultimately determine which company leads the quantum computing revolution.
Understanding these subtleties is crucial for stakeholders, investors, and policymakers as they navigate the rapidly evolving quantum landscape. 1. Technology foundations and qubit designs.
The fundamental difference between Google Willow and Microsoft Majorana lies in their qubit technologies. Google employs superconducting transmon qubits, which are sensitive to environmental noise and require extreme cooling, while Microsoft leverages topological qubits derived from Majorana zero modes, which are inherently more stable and resistant to errors. The architectural designs reflect their approaches. Google focuses on scaling the number of qubits to enhance performance and error correction, whereas Microsoft aims for a compact design that minimizes the need for extensive error correction software by utilizing the stability of its topological qubits. This foundational difference shapes the trajectory of both companies' quantum computing capabilities. 2. Error correction strategies. Error correction remains a critical challenge in quantum computing. Google Willow's strategy revolves around increasing the number of qubits to improve error correction, demonstrating significant benchmarks such as completing computations that would take traditional supercomputers eons in mere minutes. In contrast, Microsoft Majorana's architecture aims for fewer physical qubits needed for each logical qubit, relying on the intrinsic stability of its topological qubits, which naturally resist errors. Such differences in approach highlight the varying methodologies both companies are exploring in their quests for reliable quantum computations and the potential implications for the future scalability of quantum systems. 3. Scalability and commercialization goals. Both companies have ambitious scalability goals, but their timelines and approaches differ significantly. Google plans a gradual increase to over 10,000 qubits by the early 2030s, focusing initially on practical applications such as drug discovery and nuclear fusion simulations. Microsoft, however, has set a more aggressive target of achieving 1 million qubits by 2027 to 2029, with applications extending to environmental remediation and advanced materials. This disparity has raised skepticism among experts regarding the feasibility of Microsoft's timeline, particularly given the historical challenges faced in developing Majorana qubits. The differing strategies and timelines could influence market dynamics and investment in quantum technologies. 4. Industry impact and future outlook. The competition between Google and Microsoft is poised to have transformative implications across various sectors, including cybersecurity, materials science, and cloud computing. Both technologies could disrupt current encryption methods, necessitating advancements in post-quantum cryptography. The unique strengths of each approach could lead to breakthroughs in different applications, with Google potentially optimizing energy solutions and Microsoft advancing chemical modeling.
Experts suggest that while both approaches hold significant promise, a future where their methods might converge could be essential for unlocking the full potential of quantum computing.
The ongoing rivalry is expected to drive further innovation in the field, shaping the next era of computational technology.
Here are three famous historical cases that reflect similar themes of competition and technological advancement as seen in the rivalry between Google's Willow and Microsoft's Majorana in quantum computing.
1. Intel versus AMD in microprocessor development 1970s present.
The competition between Intel and advanced micro devices AMD has been a defining narrative in the semiconductor industry. Intel's dominance began in the early days of personal computing with its x86 architecture, leading to a long-standing lead in microprocessor performance and market share.
However,
AMD emerged as a significant competitor with its innovative Athlon and later Ryzen processors, challenging Intel's supremacy by offering competitive performance at lower prices. The rivalry has spurred advances in technology, driving both companies to innovate rapidly.
Intel focused on increasing clock speeds and refining manufacturing processes, while AMD emphasized multi-core architectures and integrated graphics.
This competition has greatly influenced the evolution of computing technology, much like the current race in quantum computing between Google and Microsoft, where each company is pursuing different technological approaches to achieve supremacy.
2. Apple versus Microsoft in personal computing 1980s present.
The rivalry between Apple and Microsoft has profoundly shaped the landscape of personal computing. Initially, Apple was known for its innovative graphical user interface GUI with the Macintosh, while Microsoft capitalized on the widespread adoption of its Windows operating system. The competition led to significant developments in software and hardware design,
with both companies striving for user-friendly experiences. Apple focused on aesthetic design and integration within its ecosystem, while Microsoft concentrated on enterprise solutions and compatibility.
This ongoing competition has resulted in rapid advancements in technology, software development, and user accessibility, paralleling how Google and Microsoft are pushing the boundaries of quantum computing with their respective technologies.
3. Boeing versus Airbus in commercial aviation 1990s present.
The competition between Boeing and Airbus has been a critical factor in the evolution of commercial aviation. Boeing, a long-established leader, initially dominated the market with its 737 and 747 models. Airbus entered the scene with innovative designs like the A320 and A380, challenging Boeing's market share and pushing both companies to enhance fuel efficiency, passenger comfort, and technological advancements. The competition has led to significant developments in aerodynamics, materials science,
and engine technology.
Just as Boeing and Airbus have driven each other to innovate and improve their aircraft, the rivalry between Google and Microsoft in quantum computing is likely to catalyze breakthroughs in the field as both companies strive to achieve practical and scalable solutions. These historical cases illustrate how competition among leading technology companies can foster innovation, drive advancements, and reshape industries, similar to the rivalry in quantum computing between Google and Microsoft. The future outlook for the competition between Google's Willow and Microsoft's Majorana 1 in the quantum computing space is poised to be transformative, affecting various sectors and potentially altering the landscape of computing as we know it. As both companies continue to refine their technologies, several predictions can be made regarding their trajectories, challenges,
and the implications for society. 1. Advancements in quantum technology. Google Willow is likely to make significant strides in error correction and qubit scaling.
By the early 2030s, Google aims to exceed 10,000 qubits, focusing on practical applications such as drug discovery and nuclear fusion simulations. The increased qubit count will enable more complex computations and better performance on quantum tasks that are currently infeasible for classical computers. As Google leverages its experience in software and cloud services, we may see rapid integration of quantum capabilities into existing platforms, leading to widespread accessibility of quantum computing resources.
Microsoft Majorana 1 is projected to advance its topological qubit technology, aiming for 1 million qubits by 2027 to 2029.
If successful, this ambitious goal could dramatically enhance the stability and fault tolerance of quantum computations. The inherent resistance to errors in Majorana qubits may lead to breakthroughs in applications such as environmental remediation and advanced materials.
However,
achieving this scale will require overcoming significant technical hurdles, and skepticism regarding timelines may temper expectations.
2. Industry transformation and applications. Both Google and Microsoft are targeting industries ripe for disruption. In cybersecurity, the advent of practical quantum computing could render current encryption methods obsolete, prompting a rush towards developing post-quantum cryptography. This arms race will likely lead to significant investments in security technologies to safeguard sensitive information. In materials science, Google's systems could revolutionize battery chemistry and optimize energy solutions, while Microsoft's technologies may enable the modeling of chemical reactions with unprecedented accuracy. The implications for drug discovery, climate modeling, and materials engineering could be profound, leading to innovations that significantly advance these fields. 3. Collaboration and integration.
As the competition evolves, both companies may find that collaboration could enhance their respective technologies. The integration of Google's error correction strategies with Microsoft's stable qubit architecture could yield hybrid systems that leverage the strengths of both methodologies. This could accelerate the development of practical quantum applications and facilitate the transition from theoretical advancements to real-world implementations. 4. Commercialization and quantum services. The race to commercialize quantum computing will likely lead to a burgeoning market for quantum-as-a-service platforms. Google and Microsoft are positioning themselves to offer quantum computing capabilities via their cloud services, which will democratize access to quantum resources. This will empower a broader range of industries, from pharmaceuticals to finance, to leverage quantum computing for complex problem-solving, ultimately leading to accelerated innovation cycles.
5. Public and regulatory scrutiny. As quantum computing technologies mature, public and regulatory scrutiny will increase. The potential implications for privacy and security will necessitate robust regulatory frameworks to govern the use of quantum technologies. Policymakers will need to engage with tech companies to understand the capabilities and limitations of quantum computing, ensuring that ethical considerations are integrated into the development and deployment of these technologies. 6. Education and workforce development. The advancement of quantum computing will require a skilled workforce adept in quantum mechanics, computer science, and engineering.
As the demand for quantum expertise grows, educational institutions will need to adapt their curricula to include quantum computing fundamentals.
This shift will be crucial in preparing the next generation of scientists and engineers to work in a quantum-driven economy,
ensuring that the workforce can meet the challenges and opportunities presented by this technology.
Conclusion. The competition between Google's Willow and Microsoft's Majorana 1 signifies a pivotal moment in the evolution of quantum computing.
As both companies pursue their distinct paths, the realization of scalable practical quantum computing appears increasingly within reach. The future will likely see a blend of their technologies, leading to transformative applications across various sectors, profound implications for cybersecurity, and shifts in educational and regulatory landscapes. The outcome of this competition will not only shape the future of computing but will also have a lasting impact on society as a whole.